Hello, everyone, and welcome to another GOAT seminar. Today we have the pleasure of following the talk of Krisztina, who will talk to us about fine-grained complexity of computing degree-constrained spanning trees.
Yeah, so this is a joint work with Narek, Alexander, Robert, and Hoang, and Hoang's name is underlined because he made partially the slides. And this is also the talk that I gave in Saarbrücken in July when I was visiting there, so that's why it says Saarbrücken. I forgot to change it, but anyway, so let us define the problem. So the problem that we will talk about is set of degrees minimum spanning tree, where as input we are given an n-vertex graph G that in some cases will be edge-weighted, in some cases not. And we are given a requirement function D that maps each vertex of G to some set of positive integers. And we are required to find a minimum weight spanning tree such that it respects these degree constraints so that the degree in the spanning tree of each vertex is in this set of like allowed degrees in D of V. So here is an example. We are given this graph, and for each vertex we are given some set of degrees that they're allowed to have, and yeah, all edges are of unit weight. And this is one solution, like this red. I don't know if you can see, but so we satisfy all the degree constraints. So for example, the degree of vertex A in this tree is 1, the degree of B is 3, and so on. And you see that all these degrees are in the lists of allowed degrees of each vertex. So note that we don't have, for now at least, any constraints on these like sets of allowed degrees. They can be of different sizes. They can be like any, they can contain any numbers that we wish. And of course, like it's clear that if they contain numbers that are too big, that are bigger than the maximum degree, then we don't care about them. But other than that, they can contain any numbers. And of course, if they contain 0, like we can never have some vertex of degree 0 in a spanning tree. So unless, I don't know, I guess we have an empty graph or a one vertex graph or some weird cases like that. But yeah. So here is another example. Like we are given these allowed degrees, and in this case, it is easy to see that there is no such spanning tree because so both A and D have to have degree 2, which means that we need to use all these 4 edges. But then both B and C will have degree 2, and that is not allowed. So in this case, we just say, okay, there is no solution. Another problem that we will work with is specified degree MST, which is a special case where for every vertex we are given 1 degree that is allowed, and of course that degree may be different for each vertex, but for each vertex there is only 1. And it is easy to see that this special case is NP hard by a reduction from Hamiltonian path. So if we start from some graph, we can add sort of 2 dummy vertices with requirement 1 and make everything in the graph have requirement 2. And now we see that sort of the MST that satisfies the degree requirements will actually be a Hamiltonian path because the sort of the vertices that are connected to this to these 2 added vertices will be sort of the start and end of the path, and everything else has degree 2. And the third variant that we will discuss is another special case of set of degrees MST, where this was supposed to be just D of V is equal to this set, not its cardinality. But so where for each vertex we are given a bound on its degree, so an upper bound on the degree that it's allowed to have. And this case was the most studied one, and like it has been studied, but mostly from a sort of heuristic point of view, and there are many heuristics developed from it. And also related problem where we have a global bound on the allowed degree has also been studied.
Can I jump?
Yeah.
the previous example was really, really quick for me. Why is it connected?
This one. Because it's MST.
Yeah, okay, I'm not.
Yeah. Yeah, because of the yeah, and so for this like degree constraint spanning tree where we have a global bound, we have some approximation algorithms that are pretty good, but yeah. In this talk we will talk about like exact algorithms. So what we can notice that this specified degree MST is kind of a special case of bounded degree MST. So recall that specified degrees where we only give one degree that's allowed, and bounded degrees where we give an upper bound of the allowed degrees. And of course, like this is not literally a special case as in an instance of specified degrees, not an instance of bounded degree MST, but there is a very easy reduction. So if we start from a specified degree instance, well, we can construct a bounded degree instance in sort of the most natural way by sort of just saying, okay, this is not the required degree, this is the upper bound on the required degree for each vertex. And we know that the sum of degrees in a spanning tree is 2n minus 2. So if we can just like look at the degrees that we got as input, and if they don't sum to 2n minus 2, then we immediately say, okay, this is a no instance. And if they do, then we know that actually any solution to the bounded degree MST will actually be a solution to the specified degree MST, because the only way to achieve this sum of 2n minus 2 is to take the highest possible degree everywhere. So just to recap, we have we have Hamiltonian paths that is sort of a special case of specified degree MST, where each vertex has to have degree 2 except two vertices that have to have degree 1. Then we have the specified degree where we are given an exact degree, bounded degree where we are given an upper bound, and set of degrees where we are just given a set of degrees that are allowed. So these are results from the literature about parameterized complexity of Hamiltonian paths. So we see results for cliquewidth, treewidth, pathwidth, and cutwidth. And we see that, yeah, sort of all of, they're mostly tight. So here are our results. So one thing to note is that for cliquewidth, our algorithm only works if all edges have unit weight, and for the others it works like in the general like weighted case. So we note that our bounds are kind of similar to the bounds of Hamiltonian path, where so this R here is the largest possible required degree. Just one note that in our lower bounds, R is at least 3, so we cannot use them to sort of deduce lower bounds for Hamiltonian path. And as you can see, the bounds are sort of tight or almost tight, depending on what you consider tight bounds. So, for example, for treewidth, there is this like 2r plus 2. This plus 2 is what makes it not really tight. But for pathwidth and cutwidth, we don't have this issue. So I will just briefly talk about treewidth, pathwidth, and cutwidth because they are kind of the maybe less innovative parts of our paper. So all the upper bounds, and also because kind of the solutions of them all use the same technique. So they are all like, it's more or less one algorithm that's adapted to all three cases. So for upper bounds, we use cut and count. So for pathwidth, we have just the more or less standard dynamic programming where we index by vertex degree and side of the cut. And for treewidth, we do the same, except that we have a problem with the join nodes, which we don't have in pathwidth, which kind of make our algorithm slower. And that's also where this sort of non-tight part of like 2r plus 2 comes in. And for cutwidth, we use a very similar idea because we use this like linear arrangement that sort of shows that corresponds to the smallest cutwidth. We use this to build some kind of a nice path decomposition, and then we use the pathwidth algorithm. And for lower bounds, all of them are a reduction from CSP, where one maybe interesting thing is that instead of doing the sort of standard thing and reducing one instance to one instance, we reduce one instance to sort of an OR of several instances. And yeah. So let me now sort of talk about the cliquewidth algorithm in more detail. So our result is that set of degrees MST can be solved in n to the O of k, where k is the cliquewidth of the input graph. And for some practical reasons, it's actually easier to work with NLC width, which is basically the same as cliquewidth up to a factor of 2. So what is NLC width? Well, it's similar to cliquewidth. We construct a graph using several operations. So what we are allowed to do is we are allowed to start from an initial graph. So we're the same as in cliquewidth, each vertex has a label, and the number of labels is the sort of thing that we want to minimize. So we are allowed to have an initial graph, a k-graph, which means that we just have a vertex with some label. We are allowed to take two graphs and to add edges between certain labels. So here, for example, we add all the edges from label 1 to in the first graph to label 2 in the second graph. So note that this is actually a pair, so an ordered pair 1, 2, and not a set 1, 2, because we could also have like add edges 2, 1, where we use the vertices of label 2 from here and the vertices of label 1 from here. And the third operation that we can do is relabel, where we take all the vertices with a certain label and we change these labels to all the same labels. So we take maybe all the vertices with label 1 and change it to label 2. So here is the sort of formal definition. So a k-graph is just a graph together with some labeling function on its vertices. And this join operation is the operation that we are allowed to do to construct this NLC decomposition. So basically what it does is you take two graphs, you take the disjoint union of them, then you add all the edges that are sort of described in this set of pairs alpha, and finally you relabel every vertex according to this relabeling function beta. And yeah, so an NLC decomposition is just basically an expression that says how do we construct a graph using this join operation, and the NLC width is just the minimum number of labels that we use. So what is the idea of our algorithm? Well, so the first thing that we notice is that we can somehow, if we have some sort of partial solution maybe, and we are somewhere in our NLC decomposition, so each vertex has some label, so the labels correspond to colors of the vertices, and these numbers are just the sort of how much degree we still need to add to it. What we can notice is that we can somehow group these together, because by sort of definition of NLC decompositions, all the red vertices will get the same neighbors from now on, and the same for all the blue ones and all the green ones, which means that it doesn't really matter. Like if I have some vertex that I can add to satisfy this like required degree 1 on the leftmost.
Sorry. Oh, it's the mouse, I guess. No, wait, what?
What? Oh.
Oh, the whole computer froze. Okay. Well,
It couldn't froze. The camera is going on.
Maybe
nothing reacts.
Maybe the mouse and the keyboard somehow.
Oh, wait, okay. Well, I won't be able to do anything with that, I think, because
Where does it go?
into the computer.
And that is locked.
Yeah.
Oh. Oh well.
You'll have to stick with this one.
Yes.
No.
And does the mouse work?
No, it doesn't.
Not even the mouse.
No.
But the question is where can we?
No, we can use this one for. I will solve this later.
Yeah.
Always bring us back.
Okay, so back to our problem set of degrees MST parameterized by cutwidth. So if we have some partial solution, what we're doing is the same as, I mean, basically every algorithm parameterized by cliquewidth, that we do a dynamic programming like bottom up from this NLC decomposition. And if we are somewhere in our decomposition and we already constructed some part of the solution, like let's say this, we have some tree. Okay, is this still? Yeah, it's still working. We have some tree that has some labeled vertices, labeled by these colors, and each of these vertices still has some sort of degree requirement. We still need to add some number of neighbors to it. So what we know is that all these red vertices, they will from now on behave the same. So if there is some neighbor that I can add to one of them, I can sort of detach that neighbor and attach it to another red vertex, because I know that the neighbor if it was connected to one red vertex, it was also connected to the other one, which means that I can somehow group together like all these red vertices, and I can just say, okay, I need to add two more neighbors to the red vertices, and that's it. I don't really care about how exactly to distribute. I will distribute it later, like. And the same for blue ones. So I just see that, okay, I have one blue vertex that needs two neighbors, another one that needs three neighbors. So in total, I need to add 5 blue neighbors. So basically what we can do is for each connected component of our partial solution, we can somehow simplify it. We don't really care how this component like looks on the inside. The only thing that we care is to remember to which label how many degrees I need to add, how many neighbors I need to add to each label. So what we can do is we start from this partial solution that maybe contains like these two trees that are not connected yet, but will be at some point in the future. And we can simplify it by saying, okay, the only thing I need to remember about them is that I can just sort of pretend that they are two paths. So on each path, I just have one red vertex, one blue, and one green. Moreover, I can represent this path as just a vector that's a k-dimensional vector. And another thing to note here is that I can also have some vertices of degree of requirement 0. That is not a problem in this case, because that just means that I already fulfilled their degree requirement. So how do we make this formal? Well, in order to define like a partial solution sort of more formally, we will need this notion of fixed forests. So a fixed forest is just sort of a standalone forest f and a function g that maps its vertices to the set of positive integers. So here we're not talking about our input graph at all. We just have like some forest and where each vertex of it has some some degree requirement. And the partial solution is sort of a fixed forest that lives inside our partially constructed graph. So it is a fixed forest that has the same vertex set as the this instance that we're given, and what the partial solution needs to satisfy is that the degree that we have until now, so that is the degree of in F, plus the degree G of V. So G of V is the sort of remainder, how much we need to add. So this should be a sort of allowed degree for this instance, for this vertex. And what we can construct, so from each fixed forest, we can construct a pattern that will just represent this fixed forest. So what is a pattern? Well, it will be a multi-set of vectors. So for each connected component, we will have one vector that is constructed sort of the same way as in the previous slide. So so for each component, we just remember how many, what is the degree requirement of each label, and that's it. And finally, a record of an instance consists of all patterns of all partial solutions to this instance. And this is sort of the thing that we will store. So basically, we will store a set of multi-sets of vectors. Another sort of key thing that we need to talk about is how do we combine two partial solutions? So at what point do we say that, oh, these two partial solutions can be somehow combined and they will lead to a sort of global solution? So how do we do that? Well, we look at two fixed forests and we look at some sort of set of pairs alpha. So alpha is the set that describes which edges do we add in between these two graphs. So what we want to say is, like, if I have a partial, so if I have a fixed forest F and F prime and I add edges described by alpha between them, can I find a solution? Can I sort of combine them and get a solution to sort of the whole instance? So we say that these two fixed forests are alpha compatible if there is a spanning tree that contains sort of both of them, F and F prime, and of course some edges that were supposed to be green, but they look more blue from in between, such that all the degree requirements are satisfied. So basically, they're alpha compatible if I can find a spanning tree T in this union that satisfies all the degree requirements. And of course, this sort of my solution spanning tree T should contain these two partial solutions. So I basically look at sort of, can I add edges in between F and F prime such that I get a solution? And if I can do that, then F and F prime are compatible. So another thing that is sort of useful is to talk about what does it mean that two fixed forests are equivalent. So in the sort of one of the previous slides, I said that I can replace some sort of partial solution by just these paths, and even though they look different, like I can sort of treat them the same because they are sort of from now on. I can treat them the same because whatever the fixed forest I could combine the original with, I can combine the sort of the simplified version with also. So we say that two fixed forests are equivalent if they are alpha compatible with the same fixed forests. And equivalent basically means that we can just replace one by the other and we don't lose any information. So more precisely, two fixed forests are equivalent if for every alpha and every sort of fixed forest that will be constructed in the future. So the first one, FG, and this sort of future part are alpha compatible if and only if the second one and the future are alpha compatible. So this basically just says, like, from now on, I can just replace FG by F prime G, and I don't lose any information. And sort of what we also actually do in our algorithm is we don't just simplify one fixed forest. We take a set of them and we simplify a whole set of them. So we also have some notion of, like, how do we simplify a set of fixed forests? And we do that by saying, okay, we can replace it by an equivalent set of fixed forests, where this equivalence is maybe not defined in the sort of most natural way. Like, they're not element-wise equivalent. Like, it's not that they're for every fixed forest in the sort of original set, I can simplify it and so on. But I look at really the whole set. I look at how can I extend that to a solution, and I want to sort of preserve that for the whole set. And not sort of to preserve it element-wise for each element of this set. So the definition here is that for the equivalence of sets of fixed forests is just that we need to have sort of some element in one set that is alpha compatible with the fixed forest that sort of comes from the future. And similarly, we can extend this definition to equivalence of patterns. So what is our idea? Why do we need all these notions of equivalences? Well, basically what we want to do is we want to replace so these patterns, so these multi-sets of vectors with some simpler ones that behave the same. So what are these simple patterns that we want to work with? Well, the issue is that we cannot replace it always a pattern with just one simple equivalent pattern, but we need to replace it by a sort of OR of equivalent simpler patterns. So the idea is that we have one instance and we replace it. We say that this is sort of a good instance if and only if some of these simpler patterns that we construct are good instances. So what are the simpler patterns that we want to work with? We call them nice patterns, and they look as follows. So they contain at most k big vectors, at most 1 0 vectors, and some unit vectors. So big vectors are sort of the only vectors that have entries that are larger than 1. So for each coordinate, we can have at most one vector v such that v of I is larger than 1, and in all the other vectors, this v of I needs to be 1 or 0. So this is an example. Like you can see that these two, we can have these two maybe big vectors. So for each coordinate, we have at most one vector where this coordinate is bigger than 1. And we can have like any number of unit vectors, but we don't really care about them too much because they are kind of simple, and we can sort of deal with them easily. And there are also not that many of them because, well, unit vectors is just sort of there are k of them, and each of them can appear with some multiplicity. So how do we make a pattern nice? Well, what we can do is sort of similar to this degree aggregation that I talked about before. We again do this thing that we sort of detach parts of the solution and reattach them somewhere else. So what we do is like we take parts of the spanning tree and reattach them to vertices of the same label in a different connected component. So formally, what we can do is if we have two vectors in a pattern and we look at some coordinate L, we can create two patterns, P1 and P2, where that are going to be almost the same as this initial pattern P, except for these vectors U and V that we will replace by something else. So in one of them, we replace U by just a unit vector and V by their sum. So we sort of shifted all sort of except one unit of requirement from U to V. And similarly in P2, we we shift all the requirements from coordinate L from U to V. So we again replace U and V by something, by the vectors that you can see here. And what we can show is that the pattern P that we started from is actually equivalent to this set of P1 and P2. So this basically means that the pattern that we started from kind of behaves like an OR of P1 and P. So it behaves like P1 or P2. So if there is a solution, if I can extend P1 to a solution, or if I can extend P2 to a solution, I can also extend P. So basically what we did is we started from a pattern, we replaced them by two simpler ones. So why are they simpler? Because, well, sort of for the first one, for P1, it's clear that, it's simpler because suddenly instead of U that could be any vector, we just have a unit vector. So we kind of see that we are getting closer to something simpler. And in P2, we see that, so we started with this vector U that could have any numbers inside, and in one of the coordinates, suddenly we have a 0. So we kind of see that replacing P by P1 and P2 kind of simplifies what we work with. So what our algorithm does is that we have a subroutine reduced to nice that takes as input a pattern P and outputs a family of nice patterns that are equivalent to P. So basically by using this sort of requirement shifting, we apply this several times in some sort of clever order so that we in the end replace P with a bunch of nice patterns that are equivalent to it. So all in all, the algorithm looks as follows. So we have we start with a leaf to root NLC decomposition. We use a dynamic program for the initial node, which is just one vertex with some label. It is very easy to compute its record because the record will just consist of it will be a set that will consist of vectors that will just have any allowed degree at this coordinate I. And this is sort of the part that deals with this fact that we can choose that for each vertex we can choose any of its allowed degrees. And then the sort of main part of the algorithm is how do we combine, how do we do this join operation? And well, we do it in sort of the maybe most obvious way. We take two partial solutions that we constructed until now. We look at the newly added edges that are described by this alpha, and we just guess which of the newly added edges we use. So guess here just means, of course, we try all the possible subsets of edges, and we see if this subset of edges combines with the two partial solutions of the two graphs that we started with, and if yes, so if the union of the sort of guessed set of newly added edges and the two partial solutions don't have a cycle and the degree requirements are satisfied, we just add the corresponding pattern to our dynamic programming table. Then we have to do this relabeling according to our relabel function beta, which is easy to do. There is just one simple procedure on if we have a vector, how do we relabel that? Well, basically by just moving sort of all the sort of requirements from one index to the relabeled one. And finally, when we obtain a record like this, we just use our reduced to nice subroutine to make the record nice, and then we repeat this step again. So finally, how do we know that if we have a solution or not? Well, so in the end, we will have a record at the root, and we know that our algorithm needs to return yes, if and only if at the root we have a zero vector as a record. So a zero vector here, basically as a pattern, just means that we have some partial solution where each label has requirement 0, which means that we don't need to. Which means that we fulfilled all the degree constraints. In total, we get this n to the O of k algorithm. So finally, some open problems. Well, one of them is to close this like +2 gap for treewidth, because we had 2r + 2 in the upper bound and 2r in the lower bound. Another one is so for pathwidth, treewidth, and cutwidth, we use cut and count, which means that the algorithms are random algorithms. So of course the question is, can we de-randomize them somehow? So as far as I know, like there is no sort of standard way to de-randomize cut and count, but maybe for our specific instance, it could be de-randomized. And of course, another question is, what about other parameters, other structural parameters? Yeah, we studied some of them, but there are still some for which we don't know anything. So yeah, that's it.
Thank you, Krisztina. Do you have any questions?
I'd like to ask, because I myself designed some algorithms on cliquewidth, and I was wondering what was the advantage of using NLCwidth over using cliquewidth?
Yeah, so I think in cliquewidth you're allowed to add edges between previously constructed vertices, right? And in NLCwidth you cannot do it. So I think the algorithm could be adapted to actually cliquewidth, but I think this fact that you cannot add edges in the parts that you previously constructed helps us it makes our life a bit simpler.
Any other questions?
So I wanted to ask the third thing, but then maybe more specifics. So what about parameterization by the structure of the requirements? So indeed, like bounding the maximum requirement doesn't help. So maybe something like, so if everyone requires exactly the degree, or like the upper bound is just the degree in the original graph, then it's easy.
Yeah.
So maybe if just some small number of vertices require something else and everyone else requires that degree or something like that, did you consider anything like this?
So I don't think we considered, we mostly considered like some other structural parameters, but we never considered this sort of combination of what if we didn't really consider parameterizations by these degree requirements.
Other questions?
Maybe it's not a concrete question, but if you look at set of points in the plane and you want to compute minimum spanning tree of this set of points in the plane, so this is what you can see it as a graph problem. Also, does it help? Can anything be done faster? Has it been studied?
So I don't know, but I think it would be interesting. First of all, so I also don't know if there are some bounds on. So if our graph comes from like from a set of points and Euclidean distance, I don't know if there are some bounds maybe. Yeah, I don't know because right there the main thing you gain is that you have some properties of the length of edges, right? So I don't know. I don't think they can be sort of directly combined with structural parameters to sort of gain some advantage. But I think it would be interesting to study. Yeah, like if we can say something sort of if we can do better. Yeah, maybe not in the parameterized versions because they somehow don't really take into account the lengths of edges. But maybe for the general version, maybe we can do something better. I don't know.
Other questions? Okay, maybe also some generic questions. So what about some graph classes? Is there any interesting direction or some restricted graph classes?
So I can imagine that, for example, on planar graphs, it would make sense to study this, but I don't think it has been studied because I think it is this problem was usually studied sort of from the more maybe applied point of view, where you don't know about the graph class of your graph, you just want some approximation or some heuristics. So I don't know.
I also have a question. You kind of talked a bit about the weighted version initially, but then you forgot about it. Does it change a lot?
So for cliquewidth, we actually don't know how to do the weighted version. Yeah, and for the others, I mean, we can just do it by this by cut and count, and yeah, this is like not such an issue. But yeah, for cliquewidth, we don't know how to do it because yeah, in all of these cases, we actually really use that we don't care. Like we can sort of detach and reattach the edges wherever we have vertices of the same label. But if it was weighted and these two edges were of different weights, we wouldn't be able to do this detaching and reattaching. So I don't know how we would do it.
One final small question. Okay, so let's thank Krisztina again.